In previous video, we saw that qxt can be written as a linear combination of w and the right eigenvector. Now we can also write qxt in a left eigenvector. From linear algebra, we know that when we have ax is equal to lambda x, then that x is called right eigenvector. Right eigenvector. Similarly, if we have xa is equal to lambda x, in this case, x is a vector that is on the left side of the matrix A. In this way, it is called left eigenvector. Left eigenvector. What we have written in our previous video, Rp was the right eigenvector, and we putted this value into the R, where the first column is first eigenvector, the second column is the second eigenvector, so on. Okay. Now we want to explore some other mathematics as well. Suppose that we have a left eigenvector as well. We can find out very easily. For left eigenvector, we have LP A is equal to lambda P LP. That's what we have left eigenvector. In that case, this problem, not this problem, actually the W was previously equal to, for right eigenvector, it was written as Q is equal to RW. For left eigenvector, or maybe we can write this as R inverse Q is equal to W, since we are interested in finding W first. So R inverse Q will be equal to W. One surprising fact about R inverse is this R inverse contains a left eigenvectors. You can prove it yourself. So it means that when we have R that contains right eigenvectors, then R inverse contains left eigenvectors L1, L2 up to Lm. That's what we just need to verify ourselves. So it means that WP will be equal to, which is a solution, remember that, which is a solution of decoupled equation. You probably remember this was the equation omega partial WP by partial X is equal to 0. And for that, we have a solution WPXT that will be equal to, for the left eigenvector, LP multiplied with QXT. We have written W in terms of LPQ. But remember that this Q is unknown. This Q is unknown. We cannot keep this Q over here. So what we do, we put the value of WP into our previous result over here. So that equation becomes QXT equal to P1 to M. Then we have LP, and remember that the solution is, since it is advection equation, it should have Q naught X minus lambda P T. And since we put the value of WP over here, so we have R of P. I hope you got this point. Let me just emphasize it again. We have partial WP by partial T omega partial WP by partial X is equal to 0. And then we have some initial value W naught X. When it is written in scalar form, that solution WPXT will be equal to W naught X minus lambda 1 or lambda P T, and we know that W has some relation with Q. So what we do, we simply put the value of Q over here. Okay, that's what we have over here. Now, there is one another definition which is known as simple wave. What is simple wave? First, we need to understand here P shows that P, when P is 1, then we have wave number 1. When P is 2, then we have wave number 2, so on. So when we have P is equal to 1 to M, it means that there are M waves over here. So it was just a connection where we have utilized left eigenvector Q naught as a solution, and then we have right eigenvector. And from this M waves, all M waves are adding together. The simple wave is that wave which has constant W. You see that W1 is wave number 1. If it is constant, then that wave is called simple wave. That wave is called simple wave. Very easy. Okay. For example, if we have P is equal to 1 and 2, there are two waves, and for two waves we have eigenvalues C naught and another eigenvalue is minus C naught, and the first wave has constant value, and the second wave has variable initial condition. It varies with x. Then the solution will be equal to qxt from our previous definition. From this definition, from this definition, it will be equal to w1r1 plus w2 x plus c naught t r2. In this solution, there are two waves, one wave and the second one is two wave. In these two waves, the first one is constant since it is constant. That constant, this wave is actually called simple wave as a definition. We will talk about that in future. This one is not simple wave since there is x, which w2, it depends on x. So that was our solution and the definition of simple wave. Thank you for watching.